So in today's lesson, we're going to look at models that include exponential functions, so how we can use them and how we can interpret ones that are given to us. So in the sort of scheme of lessons that we're looking at to do with this chapter, we've looked at how to sketch graphs for a to the x and e to the x. We also talked about how e was a special number, and you'll see a bit more of that in the lesson today. We also differentiated e to the kx, and if you remember why that result was important, it was the fact that the gradient of the e to the x graph was exactly equal to 1 when x was 0. So that's an important thing that we're going to use today. So today is using and interpreting models that use exponential functions. Okay, so a lot of the questions that you get where you model using exponential functions are modelling real life situations. So if we look at a couple of different examples, e to the x, where you've got a positive number in front of the x, that is a function that represents exponential growth. So a common application of that is growth of population. And if you actually go out into the real world and sort of make some recordings of numbers of how population does grow, it grows exponentially, but you'll notice that the base number that you need for that growth is actually the number e. So this is where it comes into the real world and why it is such a special number. And basically, modelling using e, because of the fact that that gradient is equal to 1, what it means is that the rate of increase of the population is proportional to the size of the population at any moment, which if you think about it, that kind of makes sense. You can also model using the function e to the minus x, when you've got a negative number in front of the power, that's going to be exponential decay. And again, an everyday example of that is radioactive decay. And again, because we're using e as our base number, what that says is that the rate of decrease is proportional to the number of atoms that are still there at that point in time. And all of this comes down to the fact that when you differentiate e to the x, you get e to the x. And remember, that differential is all about the rate of increase or the rate of decrease if you've got a negative power. Okay, so let's have a look at a couple of examples. So what I'll do is let you just read through that for a moment, copy down the example if you haven't already printed it out. You can pause this if you want to do that for a moment. So when you're given a question like this, obviously the first thing that springs out to you is the actual formula. And you can see in the formula, it's got the e to the minus 0.5t. So because it's got a negative number in front of the t, that's going to be exponential decay. Always then go on and read the context of the problem. Okay, important thing is, what do the letters represent in the formula? And also, what are their units? Because sometimes they throw things in like, this is number of people in thousands, that kind of thing. So you do have to watch out for that. So with this one, n is the number of people infected, and t is the time in years after detected. Okay, so if we have a look at the three parts of the question they're asked to do. The first bit says, how many people were first diagnosed with the disease? Okay, so if we're talking about t is the time in years after detection, hopefully what you're thinking is, okay, well, initially is when t is 0. So what we're going to do, we're going to sub t is 0 into our formula. Remember, you've got to write down the formula with t substituted into it before you put it in your calculator. E to the power 0 is obviously going to be 1, so you get 300 minus 100, you get 200. Put your units on, so 200 people. Then it says, what's the long-term prediction of how this disease will spread? So t represents the time in years. So if you're talking in long term, then what you're thinking is what's going to happen as t gets bigger or as t approaches infinity. So as t gets very, very big, this part up here, okay, is going to end up as e to the minus a very, very big number. Now remember, a negative power means 1 over, so that's going to be 1 over a very, very big number. Okay, so that is going to then approach 0. Okay, so if we look long term, as t tends to infinity, this is a sort of good way to write out your working for this. As t tends to infinity, the e part tends to 0, so n will tend to 300. So what that tells you, they want you to say in words what that actually means in the context of the problem. The disease will continue to infect people, but up to a limit of 300, and it won't ever actually reach 300, but it will approach 300. Now this is going to help you in part C, where it says to sketch the graph of n against t. Remember, you always put t along the x-axis, you always put n on the y-axis. You've got a couple of things that you can put on your graph there. Where t is 0, n is 200, so that can go on your y-axis. And then when you've got a value that is approaching something, if you remember mathematically what that means there's going to be an asymptote on your graph. So your graph is going to look like this. Because it's a minus power, you get this whole sort of exponential growth here, starting at 200 and then approaching 300, but not actually reaching it. So with these graphs, make sure you always mark on any relevant values and then dash in your asymptote as well, because then you can make the curve approach that. Okay, so one more example to have a look at. There we go. So here's a second example. Again, I'll give you a moment to read it, write it down, do pause this if you need to write it down. So here we've got the equation v equals e to the 0.4x minus 1. So you've got a positive number in front of x. So this is representing exponential growth. That's the first thing you're going to look at when you read these questions. Okay, like I said to you, have a look at the units, have a look at what the letters represent, because in this one, the V represents number of views, but it's in millions. Okay, so you've got to be careful when you give your answers to do with the number of views. X represents the days, and it's modelled by there. So find the total number of views after 5 days. Well, X is the value that represents the number of days. So what you're going to do is you're going to take your function there, your v equals 0.4x minus 1. You're going to sub in x equals 5. You're going to show your working, okay, pop it in your calculator, remember where the E button is, and then you're going to state your answer. I've put here, look carefully at the units because you must state 6.4 million, okay, views. Okay, right, find dv dx. Remember what dv dx represents. dv dx represents the rate of change of the number of views, or in this case it'll be the rate of increase of the number of views. Okay, we did in the last lesson about differentiating. So e to the power, what you do is you write exactly the same thing down again, e to the same power, and then you times it by the differential of the power. So when we do dv dx, we're going to get e to the same power, but times by a 0.4. I'll just put a little reminder there. Okay. Now, part C, find the rate of increase of the number of views after 100 days. Whenever they mention rate of increase, that is always going to be dv dx. Okay. Often in previous things you've done, you've probably had t representing time for number of days, so it might be dv dt, but this one is just in terms of x, so that's why it's dv dx. So rate of increase after 100 days, you're going to put x equals 100, but you're going to put it into your dv dx. So again, I'm going to write down my working. Okay, put it in your calculator. You get 9.42 times 10 to the 6. Okay, now this is rate of increase. Okay, so that would be that number of million views per day. All right, but I'm just going to write it down like that. That's fine. Oh, it says state the units of your answer. Oh, so I should have put on there then. Let's just add that on now. So 9.42 times 10 to the 6. So that's going to be million. Sorry about this. Million views. This is really rubbish, isn't it? But never mind. So million views okay, per day. Okay, so there we go, we've added that on now. Lovely, look at that writing. Okay, so that's my units of my answer. So it's 9.42 times 10 to the 6 million views per day. That's a rate of increase. Okay, so use your part C to comment on the validity of the model. Now that is a huge number. Okay, so if we think, would that realistically happen? Could we then have 9.42 times 10 to the 16 extra million views per day? Well, no, not really. So your answer to that bit is going to be the value of the rate of increase is too big. So the model is not valid after 100 days. You do find with exponential models that they do have a limit of the amount of time they're valid for, because they do just get bigger so very quickly. So quite often in questions you will end up saying that it's only valid for a certain range of values. Okay, right, so that's it. Hopefully you got those examples down. Hopefully you understood what I was saying there. So these are, you've got 5 questions to complete from exercise 14C. Do write out the formula first, do show substituting in, so showing all of your working, and if you are asked to draw the graph, important things to put on it are your axis intersections, and then also dash on any asymptotes if it is tending to a certain value. And if the question hasn't asked you to work that out as part of it, and then it asks you to draw a graph, you need to work that out to suss out what happens as t gets very, very big. Okay, hope that will make sense. So good luck with that.